Hi, I'm Shresh Maharaj.
Hello, my name is Amit.
In this video, we will be discussing about our project, which is FPGA for the nonlinear control of synchronous reluctance motors. Our project will focus on designing a nonlinear controller for the synchronous reluctance motor, considering the effects of magnetic saturation. This system will be based on the Power Electronics and Drives FPGA board. Now, you might be wondering, what is magnetic saturation? Magnetic saturation in synchronous reluctance motors happens when high amounts of currents are demanded by the motor. The current drawn by the motor increases when a load is put on a motor. Now, let's take an example. If your motor is running a conveyor belt and suddenly you put a very heavy load on this, when the load is applied, the speed of the rotor decreases. This has the effect of decreasing the counter EMF. And if the counter EMF goes down, the inductive reactance also decreases with respect to the value of the stator resistance. Then, according to Ohm's law, if the impedance goes down and the voltage remains constant, then the current must go up. Now, as you increase the current going through the motor, that generates a larger and larger magnetic field in order to track the reference speed. This can be seen by the magnetization curve. The magnetic field flows through the synchronous reluctance motor to produce torque. But the stator and the rotor has a limit of how much magnetic flux can actually flow through it. And once you reach this limit, the motor is in a saturated condition. At this point, the ferromagnetic material in the stator and rotor is completely full of magnetic flux and cannot take any more flux. When this happens, the motor is magnetically saturated and the efficiency drops dramatically.
I believe Shresh has given a clear explanation on what magnetic saturation is. I would now like to explain briefly on the two types of magnetic saturation. These are the self-saturation and the cross-saturation effects. So, what is self and cross-saturation? By considering the dq axis, self-saturation is when the d-axis current influences the saturation along d-axis flux path, and likewise, the q-axis current influences the saturation along q-axis flux path, whereas the cross-saturation effect is when the d and q-axis currents are able to influence saturation along either the d or q-axis flux paths. In any case, the saturation effect causes changes in the dq axis synchronous inductance. It is important to consider both the self and cross saturation effects to obtain the accurate dynamical model of the synchronous reluctance motor or any AC machine. So, it is known that almost all machines are non-linear in nature. Due to this, linear control techniques cannot be applied to the non-linear systems. This is where feedback linearization comes in. So, why feedback linearization? Feedback linearization allows transforming non-linear systems into fully or partly linear systems so that linear control techniques can be applied. Now, there are two types of feedback linearization techniques: the input state feedback linearization and the input-output feedback linearization. For the purpose of this project, we will be reviewing and implementing the input-output feedback linearization. So, what are our future works for the project? The first one is to implement the input-output feedback linearization control technique as mentioned earlier. Next is to develop the proposed control technique in the LabVIEW environment. And finally, test this in the FPGA paired board. Thank you.